Welcome to drawing a free body diagram and setting up the equations for a box sliding down a ramp. This is a skill that all levels of physics scholars could use, and hopefully I'm going to show you how to set up these problems, and hopefully this will get you a long way. So we'll figure out how to decide on the directions of the force vectors, how you could break up the force of gravity into components, and just point out what actually causes the box to slide down the ramp. First of all, we need to take a look at something, at the motion of the box. So, for example, if I were to ask you, using the axes that we have drawn here, with the x and the y, what is the motion of the box sliding down the ramp? Is it x or is it y? Well, you might say, well, wait a minute, it's both. And this poses a problem because we always have to break up our x and y motions because gravity affects the y and gravity does not affect the x motion. So to make all of our lives easier, what we have done, and you might disagree because it takes a little thing to get used to, but what we have done is that we have actually change this so instead of having the x-axis, drawn like we would in math or really just regular everyday life, we turn it. And this way, this picture matches the bottom picture below here. We're turning it so that the x direction, or the x-axis, is pointing in the x direction, and notice that it's parallel to the direction of the ramp. This way, when we say that the ramp is moving, it is moving parallel to the x direction. So when we have it done this way, our y force, our normal force, is actually following the y-axis. If there's friction in the problem, the frictional force actually follows the x-axis. The only problem is we have the force of gravity is a combination of both directions when we switch. Noticed here, when we had the regular axes, and I'm going to switch them. I'm going to switch it back to the way it was. The force of gravity actually is the only vector that is following the x-axis. Here, the normal force is in both directions, and the frictional force is in both directions. So actually, if we kept the axes this way, we could do it, but it just makes the problem more complicated, and you would end up having to do more work. So this way, we only end up breaking the force of gravity into components, and we could leave the normal force and the frictional force alone. Okay, so up until now, I am thinking that you drew the forces, and finding the forces isn't too difficult. You always have a normal force, which is perpendicular to the surface, and if your ramp is rough, you have frictional force. If it's smooth, you don't even have this force. And then every single force diagram you have has the force of gravity. You have to label the force of gravity because gravity is pulling downward. So now the question is, how do you draw the x and y components for the force of gravity? All right, well, you might remember that every single vector can be broken up into x and y components. So if you were to have, in the simplest case, if you were to have a, let's see, if you were to have a vector in the x direction, well then that is the x component. It does not have a y component. If you had a vector that was completely vertical, it would be all y component. It would not have an x component. But you have a vector that is going in both the x and the y direction. And so when we say break something up in vectors, up into its x and y components, all we are doing is saying find the x vector and the y vector that when added give you the force of gravity vector. So how do you add vectors? Well, you start by, all right, so we're going to start by drawing here the y vector, and then what do? You add by putting the tail of the x vector at the head of the y vector. So this is the force of gravity y component, and this is force of gravity x component. And yep, there we go. Just waiting for the internet to respond. Labeling a vector as the force of gravity y and the force of gravity x is not very helpful when wanting to put it into equations. Therefore, we need to relate it to other information in the problem. Now, hopefully you have learned in class that this angle is equal to that angle. I won't go into why. It's not important just right now. So the important thing is you have made yourself a right triangle using the x and y components of gravity for your x and y vectors, and or for the two sides of the triangle, and your hypotenuse is the actual force of gravity vector. So how can we write this in terms of information from the problem? Well, we mentioned, or we remember, SOHCAHTOA, and that helps us remember what the sine, cosine, and tangent are. So if I were going to do this, I would say the sine of theta equals the opposite. So right here, okay, so here is the angle. Come on, here is the angle. This is opposite to the angle. So what I am going to write is my force due to gravity, and the opposite is the x component, divided by the hypotenuse, which is just the force of gravity. If I multiply the force of gravity by each side, then what do I end up getting? I end up getting that the x component is equal to the force of gravity, the magnitude of the force of gravity, times the sine of theta. Now, same thing if I want to look at this. For cosine, here is my angle. This is the side that's next to the angle. It's adjacent. That's what adjacent means, is next to. So what I am going to do is I am going to write the cosine of theta equals, and the adjacent side is the y component. Let's make this a little more legible here. Is the y component, and this is the hypotenuse, and once again, through the magic of algebra, we will get cosine theta equals the y component. Now, don't go memorizing that the x component's always sine and the y component's always cosine. Depending on how your triangle is labeled, that could change. And if we take a look at what is actually shoving the box down the ramp, it's going to be this vector, your x component. So it's the x component of your gravity, force of gravity, that is shoving the box down the ramp. Okay, we have all of our forces drawn, we have all the components, and we have the components written in terms of variables that will use the variables of the problem. Over here, I took the liberty of turning the axes back just so we don't get dizzy, and they're the right side up, and this way we can truly see X and the Y without making any mistakes. You might want to do this, you might be looking at the ramp and you like looking at things diagonally, and that is fine. Do whatever it takes for you not to make mistakes. Okay, now this next part, we are going to set up the problem. Many students ignore this part and then they get stuck. It literally takes 1 minute, not even 1 minute, to write these things down. And so I highly suggest that after you draw a free body diagram, whatever problem you are working on, you draw your X and your Y camps, and then you use the most famous equation in physics dealing with forces. The sum of all the forces equals ma. F equals ma. Maybe you are used to using F net equals ma. Whatever notation you use it. Whatever you're comfortable with, whatever your teacher wants you to use it. Now, notice we're in X camp, so these forces and the acceleration are ones in the X direction. When you're in the Y camp, we worry about the forces and the acceleration in the Y direction, obviously. And I forgot my little net here. Okay, so actually, if you have never seen this notation, I bet you saw it in math. This means, it's Greek, it's sigma, just means the sum of. It's just fancy. Instead of writing something plus something plus something plus something, it's just fancy notation for just writing take the sum of all. Okay, so now you're just simply, you have these things written, and now you can simply just get an equation foolproof. All right, so you are going to, for your x's, you are going to look here and you are going to see having a few problems here. All right, so I am going to use FG sine of theta minus friction equals MA. Now, some of you may add up all the forces and then put the negatives in there with your numbers. Totally fine. Some of you may put your negatives in when you're writing your equation. Totally fine. You just need to make sure that you either do one or the other. All right? So, for example, if you were going to write it this way, where you put everything positive, okay, then that would mean that you need to make sure, well, you have your friction is going negative, so you would have to put a negative value in for there. Your x component is going in the positive direction. All right. And your acceleration is also positive, and this will be discussed in the next slide. All right, same for here in the y. If you add, you have your normal force, and in the opposite direction you have your y component. Why I even bought a better pen, and I can't get it to go well. All right, y component equals MA. Okay, now once again, if you are just going to take the sum of your forces, then that is fine. All right, you just want to make sure that since this is pointing downward, this is going to be a negative value when you put it in there. Fn is pointing upward. That's going to be a positive value. And actually, for this, what is the acceleration? Is the box bouncing up and down in the y direction? It's really not. It's not moving in the y direction. All right, so it's not accelerating, which means that really it's going to equal 0. This is true for any box or, something sliding down a ramp. If it's not bumping up and down, which pretty much it's usually not, if it's not bumping up and down, then it's not moving in the y direction, and therefore it's not accelerating in the y direction. So your A equals 0. You might have encountered something tricky on your homework. Depending on the way you draw your ramp, you have to make your acceleration sign different. You have to make this, I should say, the sign of your acceleration. You need to make that slightly different. So if you drew your ramp this way, your x, the box is going down in the positive x direction, which means that its velocity is positive. Since it's speeding up, velocity is the same acceleration as same sign as the acceleration, so your acceleration is positive. Here, your box, if you drew your ramp this way, your box is sliding down. This is the negative x direction, so your velocity would be in the negative direction, speeding up, which means that your acceleration would be negative. So in this case, your acceleration, you need to put a negative acceleration value into there. All right. Now, once again, so you don't. Now, I want to avoid you making mistakes. So, if you are writing the sum of your forces, say in the x equals ma, if you starting with this, then if you write your equations, so let's just take this for example. So you're going to have this is your force of gravity. This is your normal force. This is the force of gravity, I should say, in the x direction, right? And this is the force of friction. Okay, I've already broken it up into components. We went through this. So these are the 3 vectors that you would be working with. I would put negative force of gravity x component because it's moving in the negative direction. I would put positive friction, and I would have it equal to negative ma because the a is negative. Now, if you are one to make your equations so that everything is positive, so for example, you are going to write this equals ma, then you need to make sure that you are putting a negative value in for here because it is moving in the negative direction. You would put a positive value here because friction is pointing in the positive direction, and you would put a negative value in for your acceleration. So even if the problem says the acceleration is a certain value, you need to decide what sign it is. They are just telling you the magnitude. All right. So these 2 ways of doing it are the same. It just depends on which way your teacher introduces it in class. once you get your x and your y equations, you still might get stuck. If they're asking for the coefficient of friction, or if they're asking for the mass of the block, you might be in trouble. So this is where the fun equation comes in. This is your force of friction, or in the other slide, I just made it little f, depending on the notation that your book uses. Mu is the coefficient of friction, and so the rougher the surface, the bigger the mu, or the bigger the coefficient of friction. And of course, Fn is your normal force. Okay, I now wrote down two equations that it's very possible that you have in a problem. Okay, so the x equation and the y equation. And now let's suppose that you have to solve for the mass, or you have to solve for the coefficient of friction. If you look at these two equations, they don't have those in there. But if you use the fun equation, you can find it. So if you're looking at your y equation, you can substitute the normal force, and all I did was divide both sides by mu. That's how I got this equation right here. So you could substitute that, or you could take your force of friction here and substitute mu Fn or mu mg, because mg equals the normal force in this problem. And you could substitute those for your force of friction. And this way you can solve for whatever variable you need. Before leaving the slide, I just want to make sure that that you pay attention to really what this equation means. And really, in words, this is what it means. It just simply says that the more force that the surface has to put on an object, okay, so if it's heavier or if you're shoving down on it, that causes the surface to push up on it more. So your normal force is bigger. So when this happens, you're going to have a harder time pushing something, or the friction's going to be bigger. To summarize, to successfully draw vectors for a box sliding down a ramp and to solve the problem, redraw the x and y axis so the x-axis is parallel to the surface of the ramp. Draw all the forces acting on the box. Break up any diagonal vectors into their x and y components. So in this case, it's the force of gravity vector. Use the vectors to make your x and y equations needed to solve the problem. Do not neglect to separate your x and your y equations. This will help you greatly. And 5, once you form those equations, if you get stuck, see if you could use the fun equation to help you out. I always, always, always beg my students to redo your homework problems. That is the best way to study for a quiz or a test. If you can do a problem without looking at any answers, and you're not memorizing, and you can explain each step of the problem as you go, then you know it and you will do just fine on a quiz or a test. And always remember, hardworking scholars can do anything.